Hello students, welcome to this lecture, One Probability. So in this lecture, we will discuss miscellaneous examples, example number 9 to 12 and exercise 1 to 2. This is disclaimer. So first we will cover NCERT miscellaneous examples 9 to 12. And then we will discuss NCERT miscellaneous exercise question number 1 to 2. So make sure you have with your notebooks and pens ready. So look at first question here, example number 9. Okay. So what we have given here in this example, we have on her vacations, Veena visits 4 cities A, B, C, and D in a random order. Then we have asked, what is the probability that C visits A before B? And second, we have asked, what is the probability that C visits A before B and B before C? Okay. So students, first of all, try it yourself. So you have 40 seconds to try to solve this question. Then we will provide the solution. Okay, students. Now we will solve this question. So first of all, find number of arrangements in which Veena can visit 4 cities A, B, C, and D. Okay. So what is the number of arrangements in which Veena can visit 4 cities? So the number of arrangements in which Veena can visit 4 cities A, B, C, or D is 4 factorial. Okay. So here 4 factorial, and 4 factorial is basically equal to 24. Okay, that is 24. So now what is the number of element in sample space S here? So here are the number of arrangements in which Veena can visit 4 cities is 24. So therefore number of element in sample space S is 24. Clear? And since the number of elements in the sample space of the experiment is 24 and all these outcomes are considered to be equally likely. So what does mean equally likely? Equally likely means all of these outcomes have equal chance to occur. Okay, so this type of outcomes are called equally likely outcomes. Clear? So since the number of elements in the sample space of the experiment is 24, all of these outcomes are considered to be equally likely. So was our sample space for this experiment is okay. So what is the sample space of this experiment? So here you can see Veena can visit first A city, then second B, then third C, then fourth D. Okay, and then here Veena can visit first city A, then B, then D, then C. Okay, and like this. So you will obtain such 24 elements in sample space S. Okay, so this is our corresponding sample space for this experiment. So note this, note this sample space. So now let the event C visits A before B. So this event be denoted by E. Okay, so we first let the event C visits means Veena visits A city before B city be denoted by E. So what will be the event E? So the event E will contain A B C D, C A B D, D A B C, A B D C, C A D B, okay, and D A C B, A C B D, A C D B, A D B C, C D A V, D C A V, or ADCV. Okay, so here you can check here Veena can visit ACT before BCT. Okay, so the event E containing these sample point. So how many element in number in event E? So you can count number of elements in event E is basically 12. Okay, and here total number of elements in sample space is 24. So what is the probability of E? So probability of E is nothing but equal to number of element in event E divided over number of element in sample space S. Okay, so n of E is 12 and n of S is 24. So probability of E is 12 over 24. And after simplifying, you will obtain this is equal to 1 by 2. So probability of the visits A before V is 1 by 2. Clear? Now we let the event Bina visits A before B and B before C. Okay, and this event be denoted by F. So now how can you find the event F as a set? Okay, so the event F containing this sample point A, B, C, D. Okay, here you can see Bina visits A before B. Okay, and B before C. Okay, and this is also okay. This is also is containing in event F, because here you can see event A, the Vina visits A before B and B before C. Okay, so similarly you will obtain ABDC, ADBC. So F will contain ABCD, DABC, ABDC, and ADBC. So F contains 4 sample point here. Okay, so number of element in the event F is 4. Now we will use definition of probability. Okay, that is probability of F is equal to number of element in event F divided over number of element in sample space S. Okay, so here you can see a number of element in the event F is 4. Okay, and number of element in sample space S is 24. So you will get probability of A, this is equal to 4 over 24 and this is equal to 1 by 6. Clear? So probability of Veena visits A before B and B before C is 1 by 6. So I hope it is clear to all of you. Simply we first first we denoted the sample space is okay, and we found the number of element in sample space is, and then we let here the event E, that is here Veena visits A before V. Okay, and then we calculate probability of E, this is equal to 1 by 2. And then second case, the event we let here A before V and B before C by F. Okay, and here F contains 4 sample point, and then we found probability of F is 4 by 24 and this is equal to 1 by 6. Clear? So now let us move to the next example. So first of all, read the example very carefully. So what we have given in this example, so let's see. So here we have to find the probability that when a hand of 7 cards is drawn from a well shuffled deck of 52 cards, it contains all kings. Okay, first 1 kings, second 3 kings, and the third at least 3 kings. Clear? So you have to find the probability that when a hand of 7 cards is drawn from a well shuffled deck of 52 cards and it contains 1 kings, okay, and then 3 kings, then at least 3 kings. So students, first of all, try it yourself. You have 40 seconds to try to solve this question and then we will provide the solution. Okay, now we will solve this example. So here we have to draw 7 cards from a well shuffled deck of 52 cards. Okay, so we have to draw 7 cards out of 52 cards. So in how many ways we can draw 7 cards out of 52 cards? The total number of possible hands, okay, of 7 cards is drawn from a well shuffled deck of 52 cards is 52C7. Okay, so this is our total number of possible hands. And now we will find probability that when a hand of 7 cards is drawn from a well shuffled deck of 52 cards and it contains all kings, means it contains 4 kings. Okay, so in how many ways you can you can draw 4 kings out of 52 cards? Okay, so here you have 4 kings. Okay, so out of 4 kings you have to draw 4 cards. Okay, and other 3 cards, okay, other 3 cards must be chosen from the rest 48 cards. Okay, so the number of hands with 4 kings, this is nothing but equal to 4c4 multiplied with 48c3. Okay, so this is our number of hands with 4 kings. How we get? Because we have to draw 7 cards. Okay, and out of these 7 cards, 4 cards are kings and other cards must be chosen from the rest 48 cards. Okay, and we can do this in 4c4 into 48c3 ways. So what is the probability? What is the probability that when a hand of 7 cards is drawn from a well shuffled deck of 52 cards and it contains all kings? Okay, so probability a hand will have 4 kings. I mean 4 kings means all kings. Okay, because in a well shuffled deck of 52 cards, there we have 4 kings. Okay, so probability of a hand will have 4 kings. This is equal to basically this is equal to 4c4 multiplied with 48c3 divided over 52c7. Okay, and now calculate it. So you can easily calculate it by using this formula NCR equal to n factorial divided over r factorial times n minus r factorial. Okay, so if you use this formula and if we calculate, then you after simplifying you will obtain probability of a hand will have 4 kings is 1 upon 7735. Okay, so you can easily calculate it and then you will obtain this is equal to 1 over 7735. Clear? So probability of a hand will have 4 kings is 1 over 7735. Now we will find probability that when a hand of 7 cards is drawn from a well shuffled deck of 52 cards and it contains 3 kings. Okay, so number of hands with 3 kings, okay, and 4 non king cards can be selected in 4c3 multiplied with 48c4 ways. Okay, so number of hands with 3 kings and 4 non king cards, this is nothing but equal to 4c3 multiplied with 48c3 c4. Okay, so in this way you can uh, you can draw 3 kings and 4 non king cards from a well shuffled deck of 52 cards. So therefore, probability of 3 kings. Okay. So probability of a hand of 7 cards is drawn from a well shuffled deck of 52 cards and it contains 3 kings, that is equal to basically 4c3 multiplied with 48c4 divided over 52c7. Okay. And now calculate it by using the formula NCR equal to n factorial divided over r factorial times n minus r factorial. Okay, and then if you will get by simplifying this is equal to 9 over 1547. So probability of 3 kings is 9 divided over 1547. Clear? Now, probability of at least 3 kings. Okay. So probability of at least 3 kings. Okay, that means basically probability of 3 kings or 4 kings. Okay. So at least means it must contain 3 kings. Okay. It might be 4 kings. So this means probability of 3 kings or 4 kings. So we've already known that probability of A union B. Okay, A union B. This is equal to probability of A plus probability of B when A and B are mutually exclusive events. Okay, so here we can see uh, probability of at least 3 kings. This means probability of 3 kings or 4 kings. Okay, so this is equal to basically probability of 3 kings plus probability of 4 kings. Okay, and now you can easily find probability of at least 3 kings. Okay, so just put the value of probability of 4 kings and probability of 3 kings. Okay, so after putting the values of probability of 4 kings and probability of 3 kings, you will obtain probability of at least 3 kings. This is equal to 9 over 1547 plus 1 over 7735. Okay, just add them and then you will obtain answer. So probability of at least 3 kings, this is equal to 46 divided over 7735. Clear? So we found here probability a hand will have 4 kings is 1 upon 7735, and probability of 3 kings is 9 upon 1547, and probability of at least 3 king is equal to 46 divided over 7735. Clear? So I hope it is clear to all of you. So now let us move to the next example. So in this example, we have if A, B, C are 3 events associated with a random experiment, then we have to prove that probability of A union B union C, this is equal to probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of A intersection C minus probability of B intersection C plus probability of A intersection B intersection C. Okay, so for 2 events we already proven we've already proved probability of A union B. This is equal to probability of A plus probability of B minus probability of A intersection B. Okay, and now for 3 events. For 3 events, we have to prove here probability of A union B union C. This is equal to probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of A intersection C minus probability of B intersection C plus probability of A intersection B intersection C. Okay, so students, first of all, try it yourself. Try to prove this example. So you have 40 seconds. Try to solve this example, then we will provide the solution. Okay, students, now we will prove this. So what we have given here? So we have given A, B, C are 3 events associated with a random experiment. Okay, and then we have to prove that probability of A union B union C, this is equal to probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of B intersection C minus probability of A intersection C plus probability of A intersection B intersection C. Okay. So now first consider event E, this is equal to basically union of event B and C. So E event, this is equal to B union C. And then so that probability of A union B union C, and this can be written as probability of A union E. Okay, so we consider here the event E is equal to B union C, and then probability of A union B union C, this is equal to probability of A union E. And then it implies probability of A union B union C, this is equal to probability of A plus probability of E minus probability of A intersection E. Okay, basically we used here probability of A union E, this is equal to probability of A plus probability of E minus probability of A intersection E. Okay, so now naming this equation, equation number 1, and now probability of E, this is equal to probability of B union C. Okay, because here we considered event E, this is equal to B union C. Okay, so probability of E, this is equal to probability of B union C. And now we using here same formula, probability of B union C, this is basically equal to probability of B plus probability of C minus probability of B intersection C. Okay, so it implies probability of E, this is equal to probability of B plus probability of C minus probability of B intersection C. So naming this equation, equation number 2. And also here A intersection E. So just put here the event E, this is equal to B union C. Okay, so A intersection B union C. So just using here distribution property of intersection of sets over the union. Okay, so A intersection B union C, this can be written as A intersection B union A intersection C. Okay, so we used here distribution property of intersection of sets over the union. Okay, so note this point. This point is very important point for this example. Okay, so pay close attention to this part. So A intersection E, this is equal to A intersection B union A intersection C. And thus probability of A intersection E, this is equal to probability of A intersection B plus probability of A intersection C minus probability of A intersection B intersection of A intersection C. Okay, just you can consider A intersection B as some event. Okay, and B intersection is another event. Then apply probability of A union B, this is equal to probability of A plus probability of B minus probability of A intersection B, this formula. Okay, so just we will obtain probability of A intersection E, this is equal to probability of A intersection B plus probability of A intersection C minus probability of A intersection B intersection of A intersection C. Okay, now simplify the right hand side. Okay, so this right hand side can be written as probability of A intersection B. Okay, same as previous one, and same as previous one, probability of A intersection C. Okay, just unchange these two terms, and then you can write this term as probability of A intersection B intersection C. Okay, so probability of A intersection B intersection of A intersection C, this can be also written as probability of A intersection B intersection C. Now naming this equation, equation number 3. So now use equation 2. Okay, that means probability of E, this is equal to probability of B plus probability of C minus probability of B intersection C, and probability of A intersection E, this is equal to probability of A intersection B plus probability of A intersection C minus probability of A intersection B intersection C. Okay, so using equation 2 and 3 in equation number 1. Okay, so now put the values. Okay, put the equation values in equation number 2 and 3 in equation number 1, then we will obtain here probability of A union B union C. This is equal to probability of A plus in place of probability of E, we can write here probability of B plus probability of C minus probability of B intersection C. Okay, just write in place of probability of E this expression probability of B plus probability of C minus probability of B intersection C. Okay, and uh, then replace the value of probability of A intersection E. So what is the value of probability of A intersection E? So probability of A intersection E, this is equal to basically probability of A intersection B plus probability of A intersection C minus probability of A intersection B intersection C. Okay, so if we now rearrange this equation, and then we will obtain basically probability of A union B union C. This is equal to probability of A plus probability of B plus probability of C minus probability of B intersection C minus probability of A intersection B minus probability of A intersection C plus probability of A intersection B intersection C. Okay, so how we approached here? So first we consider the event E is B union C. Okay, so we have written here 3 events as 2 events first. Okay, and then we apply probability of A union B. Okay, formula for probability of A union B, and then we write here probability of E equal to basically probability of B union C. Okay, then we apply the formula probability of B union C, and then after simplifying, we will obtain the required equation, that is probability of A union B union C. This is equal to probability of A plus probability of B plus probability of C minus probability of B intersection C minus probability of A intersection B minus probability of A intersection C plus probability of A intersection B intersection C. Okay, hence proved. So I hope it is clear to all of you. So now let us move to the next example. So student, first of all, read the example very carefully. So what we have given in this example, first see, and then see what actually we have to find. Okay, so in a relay race, there are 5 teams: A, B, C, D, and E. So here we have 5 teams in a relay race. Okay, and then we have asked what is the probability that A, B, and C finish first, second, and third respectively. Okay, so first you have to find probability that A, B, and C finish first, second, and third, and then we have to find what is the probability that A, B, and C are first 3 to finish in any order. Okay, here it may be first, second, third, or it may be first, third, second. Okay, in any order. So here assume that all finishing orders are equally likely. Okay, so first of all try it yourself this example, and then we will provide the solution. So you have 40 seconds to try to solve this question, and then we will provide the solution. Okay, students, now we will solve this example. So we have given here in a relay race, there are 5 teams: A, B, C, and D. A, B, C, D, and E. Okay, and then we have asked what is the probability that A, B, and C finish first, second, and third. Okay, so we have to find the probability that A, B, and C finish first, second, and third respectively. And then we have to find what is the probability that A, B, and C are first first three to finish in any order. Okay, so let's solve this example. So if we consider first the sample space consisting of all finishing orders in the first three places. Okay, so first we consider here the sample space basically consisting all finishing orders in the first three places. Now here we have 5 teams. Okay, and out of 5 teams here are 3. Okay, A, B, C finish first, second, and third. So what will be the probability that A, B, C, and C finish first, second, and third respectively? Okay, so we will have here 5p3. So here we will use permutation formula, that is NPR equal to n factorial divided over n minus r factorial. Okay, so what is the value of 5p3? So 5p3, this is equal to basically 5 factorial divided over 5 minus 3 factorial. Okay, and it can be written as 5 factorial divided over 2 factorial, and 5 factorial can be written as 5 into 4 into 3 into 2 factorial. Okay, and then 2 factorial will be cancel out, and then we will obtain 5p3. This is equal to basically 5 into 4 into 3, and this is equal to 60. Okay, so we will have 60 sample points. So each with a probability of 1 by 60. Why? Because you can see here all finishing orders are equally likely. Equally likely means all finishing orders has equal chance to occur. Okay, so here we have 60 sample points. So then probability of each outcomes will be 1 by 60. Now we will find the probability that A, B, and C finish first, second, and third. Okay, so first let first here see A, B, and C finish first, second, and third respectively. Okay, so there is only one finishing order for this. So A will finish first, then B will finish second, and the C will finish third. Okay, so this is only one finishing order, and this finishing order is basically A, B, C. So now, what is the probability that A, B, and C finish first, second, and third? Okay, so in sample space, we have 60 sample points. Okay, and out of these 60 sample points, there is only one finishing order for A, B, C finished first, second, and third. Okay, and this is basically A, B, C. So probability of A, B, and C finish first, second, and third respectively is equal to basically 1 by 60. Okay, so probability of A, B, and C finish first, second, and third respectively is 1 over 60. Clear? Basically we used here uh, classical definition of probability, that is probability of an event. This is equal to basically number of elements favorable to the event E divided over number of elements in sample spaces. Okay, so here you can see in sample space we have 60 sample points, and out of these 60 points there is only one finishing order for A, B, C finish first, second, and third. Okay, so therefore probability of A, B, and C finish first, second, and third respectively is equal to 1 by 60. Clear? Now look at second part. So in this example, in second part we have asked what is the probability that A, B, and C are first 3 to finish. Okay, so A, B, C are the first 3 finishers. So here in any order, it may be in any order. Okay, so A, B, C are the first 3 finishers. So there will be 3 factorial arrangement for A, B, and C. Okay, so A may be first, B may be second, C may be third. Okay. Or A may be second, B may be first, C may be third. Okay. So you will obtain basically 3 factorial arrangements for A, B, and C. Clear? So therefore, the sample points corresponding to this event will be 3 factorial in number. Okay. So we will have 3 factorial numbers in sample points will be 3 factorial. So what will be the probability that A, B, and C are first 3 to finish? So here here you can see in this event we have 3 factorial sample points. Okay, out of total 60 sample points. Clear? So probability of A, B, and C are first 3 to finish. This is nothing but equal to 3 factorial divided over 60. Okay, and you all know 3 factorial, this is equal to basically 6. Okay, so this is equal to 6 over 60, and this is equal to 1 by 10. So therefore probability of A, B, and C are first 3 to finish is 1 by 10. So students, I hope it's clear to all of you. So now let's move to the next one. So here we will discuss miscellaneous exercise question number 1. Okay, so first read the question very carefully. So in this question we have a box contains 10 red marbles, 20 blue marbles, and 30 green marbles. 5 marbles are drawn from the box. Then what is the probability that one will be blue? Okay, and then what is the probability that at least one will be green? So how many marbles you have? So a box contains 10 red marbles, 20 blue marbles, and 30 green marbles. Okay, so total you have 60 marbles. Okay, and out of 60 marbles you have to draw 5 marbles. So 5 marbles are drawn from the box in how many way? Okay, so let's think about this. So how would you approach this question? So think about this for a moment. You have 40 seconds to try to solve this question, and then we will provide the solution. Okay, students, I hope you try to solve this question. So now we will solve this question. So first, uh, see how many marbles in this box. So this box contains 10 red marbles, 20 blue marbles, and 30 green marbles. Okay, so total number of marbles, this is equal to 10 plus 20 plus 30. Okay, and this is equal to 60. And now we have to draw to draw 5 marbles. Okay, so 5 marbles are drawn from the box. So out of 60 marbles, 5 marbles can be drawn in 60C 5 ways. Okay, so number of ways of drawing 5 marbles from 60 marbles is 60C5. Now we have to find probability that all will be blue. Okay, so we have to find probability that all the 5 marbles, okay, 5 marbles will be blue. So all the drawn marbles will be blue if we draw 5 marbles. out of 20 blue marbles. Okay, so we have in a box 20 blue marbles, and we are drawing 5 blue marbles from this box out of 20 blue marbles. Okay, so 5 blue marbles can be drawn from 20 blue marbles in 20C5 ways. Okay, so 20C5 ways we can draw 5 blue marbles out of 20 blue marbles. So now probability that all marbles will be blue, this is basically equal to number of marbles. Okay, number of ways, number of ways 5 blue marbles can be drawn from 20 blue marbles divided over number of ways of drawing 5 marbles from 60 marbles. Okay, and this is equal to 20C5 divided over 60C5. So probability that all marbles will be blue, this is equal to 20C5 divided over 60C5. Clear? And now we will find probability that at least one will be green. So in the box, how many green marbles are there? So in the box there are 30 green marbles. Okay, so number of ways in which the drawn marble is not green. So we have marbles which is not green. Basically we have 30 marbles like that. Okay, so number of ways in which the drawn marble is not green, this is basically 20 plus 10 C5. Okay, so this is 30C5. So 30C5 in this ways we can draw marble which is not green marble. Okay, and now probability that no marble is green, this is basically equal to number of ways in which the drawn marble is not green divided over number of ways of drawing from 5 marbles from 60 marbles. Okay, and this is equal to basically 30C5 divided over 60C5. Okay, so probability that no marble is green is 30C5 divided over 60C5. And now we will use probability of complement of event. Okay, so we will know probability of a complement, this is equal to 1 minus probability of event a. Okay, so for finding probability that at least one marble is green, it can be find as 1 minus probability that no marble is green. Okay, so probability that at least one marble is green is nothing but equal to 1 minus probability that no marble is green. Okay, and we already found probability that no marble is green is 30C5 divided over 60C5. Okay, so probability that at least one marble is green, this is equal to 1 minus 30C5 divided over 60C5. Okay, and the probability that at least one marble will be green will be 1 minus 30C5 divided over 60C5. So students, I hope it is clear to all of you. Okay, so now let us move to the next question. So now look at question number 2. So in this question, what we have given, so 4 cards are drawn from a well shuffled deck of 52 cards. Okay, so we are drawing 4 cards out of 52 cards. Then we have asked what is the probability of obtaining 3 diamonds and 1 paid. Okay, so students, first of all, try it yourself. You have 40 seconds to try to solve this question, then we will provide the solution. Okay, students. Now we will solve this question. So first, see, in how many ways we can draw 4 cards from 52 cards. So number of ways of drawing 4 cards from 52 cards is equal to 52 C4. Okay. And in a deck of 52 cards, there are 13 diamonds and 13 pairs. Okay. So you should all know how many diamonds cards are in a well shuffled deck of 52 cards, and how many spades cards in a well shuffled deck of 52 cards. Okay, so in a deck of 52 cards, there are 13 diamonds and 13 spades. So now we can find number of ways of drawing 3 diamonds and 1 spade. Okay, in 13C3 multiplied with 13C1 ways. Okay, in this ways, we can draw 3 diamonds cards and 1 spade card. And thus the probability of containing 3 diamonds and 1 spade, this is equal to basically 13C3 multiplied with 13C1 divided over 52C4. Okay, so number of ways of drawing 3 diamonds and 1 spade is 13C3 multiplied with 13C1. Why? Because you can see in a well shuffled deck of 52 cards, there are 13 diamonds. Okay, and out of 13 diamonds, we have to draw 3 diamonds. Okay, so out of 13 diamonds, 3 diamonds cards can be draw can be drawn in 13C3 ways. Okay, and out of 13 spades, we can draw 1 spade in 13C1 ways. Okay, so thus the probability of obtaining 3 diamonds and 1 spade, this is equal to 13C3 multiplied with 13C1 divided over 52C4. Okay, so this will be our answer for this question. So I hope it is clear to all of you. So that's all for today's lecture. So thank you very much to all of you.